Specifiers, manufacturers, and designers may have to make decisions at the material and chemical level. Increasingly, material and chemical assessments are being combined with life cycle analysis to understand energy and material use. Our cell phone case illustrates this. While there are many different materials that a smartphone case could be made of, such as metal, fabric, or plastic, let's focus on materials made from polymers for soft, flexible phone cases. Polymers can be natural, like rubber, or synthetic, like many plastics. All polymers are chains of molecules strung together. Polymerization is the process of combining many small molecules, known as monomers, into a covalently bonded chain or network. The way these atoms are strung together determines the properties of the material. These properties determine the performance of the substance. In a circular economy, designers will want to widen their criteria for performance to support circular economy goals. Technical performance and health performance, both human and environmental, should go hand in hand. Aligning the goals of the circular economy with a selection strategy for materials will shape the criteria used. For example, if recycling of the product is important, then it may be better to choose a polymer that can be broken down or depolymerized and reformed into a new product after its first use. Here are some typical criteria that represent both technical and health performance objectives. Mechanical strength, longevity, cost, ease of manufacture, functional performance, and finish are all technical performance criteria that designers consider. Similarly, human health criteria like food safety, environmental fitness, and sustainable material production are also important performance criteria. To meet the goals of human health and environmental performance, designers and specifiers will increasingly look at hazard endpoints, screening products and materials for things like carcinogenicity, mutagenicity, reproductive toxicity, developmental toxicity, endocrine activity, acute toxicity, sensitization, irritation, and other health effects, persistence, bioaccumulation, aquatic toxicity, ecotoxicity, physical hazard, and other physiochemical traits. Typically, all these hazard traits are looked at in light of when people would be exposed to the substance and to what degree. The inherent hazard of the chemical, plus how and how often someone is exposed to it, plus the vulnerability of that person, all add up to risk. Technical performance is then weighed with risk assessment to make a final choice of the best substances to use or the ones to avoid. You would start a typical hazard assessment by identifying the compounds of interest. Next, you would search for authoritative lists about chemicals, scanning the scientific literature and filling information gaps by analyzing comparables, analogous materials, and similar functional groups. Let's go back and look at our smartphone case example. There are 3 typical materials used for basic flexible smartphone cases: silicone, hydrocarbon polymer, and thermoplastic urethane. Silicone is a synthetic polymer typically formed in a compression mold, painted, UV cured, and sealed. It is commonly used in industry for a wide range of applications because of its superior material performance. Waterproof, shock-absorbing, and non-reactive with chemicals, silicone is insulating, has low thermal conductivity, and is resistant to oxygen, UV, and ozone degradation. The chemical structure of silicone is the key to this performance. Silicone has long but strong bonds at wide angles within the molecule chain that make it flexible but stable and persistent. Unlike many plastics formed around a carbon backbone, silicone is formed around chains of siloxane, composed of silicon and oxygen. Silicone is FDA approved for food contact and cooking. It is not classified as hazardous waste, is not toxic to aquatic or soil life, is stable at a wide range of temperatures, and biodegrades fairly easily. However, certain forms of siloxane have been linked to problems such as reproductive, neurological, and immune effects, as well as bioaccumulation. At very high temperatures, above 200 degrees C, silicone releases formaldehyde, a toxic substance and probable human carcinogen. When a designer makes the decision about which material to use for a smartphone case, they would include this information in a report card that considered human health as well as technical performance. The designer would compare silicone to two typical alternatives, hydrocarbon polymer and thermoplastic urethane, or TPU, for hazard endpoints and risk throughout the product's life cycle, as well as cost and feasibility of using the alternative material. It is also important to consider where in the life cycle of the product such cautions occur. For instance, in the case of silicone and most synthetic polymers, it is at the manufacturing stage and end-of-use stage that most hazards present themselves. Green chemistry approaches of material avoidance or more benign substitution come well upstream of interventions like engineering or administrative controls. The goal is to avoid materials or substitute benign materials before a substance is specified or manufactured. Green chemistry offers a range of potential benefits and innovations, including the reduction of toxicants, the use of more common and less expensive feedstocks, more efficient processes, and the design of recyclable materials. Ultimately, this approach will be critical to the kind of integrated and interconnected systems envisioned for the new circular economy.